All right. Good evening, everyone. My name is Charles McNabb, and this is my Lab 3 report. So, essentially, what we were doing here was collecting data to calculate the magnetic dipole moment of a bar magnet. Now, how we went about this was we first had to download a magnetometer app and then go ahead and use that app to align a meter stick with Earth's magnetic north. This was in order to make sure that Earth's magnetic field wouldn't actually have too much of an effect on our data. We then ran our phone, or well, I then ran my phone along this meter stick in different orientations to find the actual location of the magnetometer in my smartphone, just to get the most accurate data. And then I used that app to measure the magnetic field at various distances, I guess R values, and then moving my phone up, down, parallel, sideways. If you name it, I probably moved my phone in that direction just to get as many values as we could. Now, and then this equation below is for distance dependence. It's for the magnetic field of a bar magnet, but it's involving distance dependence, which is what we went ahead and measured here. Now, this was the data that I collected. You could see over here that this is those magnetic field values at various locations, which then came into factor down here. Now, all of this comes down to here, where we have the the vector for magnetic field, as well as the net value for magnetic field. But what we're looking at right now is the results of this graph, which we went ahead and used in calculation to find the magnetic dipole moment. Now, we know I couldn't get the vector arrow thingy above here, so we're just going to know that that's a vector. We know that the magnetic field is calculated as such, and we also know that through our lab instructions that this slope value is correlated with this equation here. And so this was our slope value here, and we could see that n is actually just this. And I went ahead and made the assumption that n is fairly close enough to just call it -3. We'll see where that comes in later. Now, back calculating for k here with the matching it to the y-intercept, we found that the value of k is this. Now, using the equation here, we can equate the two. While knowing that n is equal to -3, we could actually go ahead and cancel out the r values, leaving us with this pretty handy equation. And then back calculating from there, we just have that our magnetic dipole moment is 2.18. That was the experimental magnetic dipole moment. Now, just getting into the coding side of things, here is my code for the magnetic field of a dipole. Pretty easy. We were given this equation, so yeah, not much to go over there. And then here are my magnetic field arrows. Here we were just using this data up here to come down and create arrows representing magnetic field at different orientations and positions. And the scale I used here was like 10,000, and that worked pretty well for me. Moving forward, this is just the net magnetic field at 45 degrees, which is honestly a little bit annoying to calculate, but yeah. Anyway, this is the computational model. Again, the scale I used was 10,000, so it could have been a little bit bigger, but I think I'm going to live with it. And so what we get is this, model right here. Now, moving on to just some important questions. The first one, what if you hadn't orientated your experiment to account for magnetic north and had laid out the meter stick at some intermediate angle with respect to Earth's magnetic field? How would the results have changed from that? So, placing the meter stick in the way that we did allowed us to negate a lot of the effects that Earth's magnetic field would have on our experiment. We figured that out when X was essentially 0. That's how we knew where that Earth's magnetic field lies. So if we hadn't done that, then our X values could have totally been skewed. And then if we were to stick two identical magnets together and run the experiments again, how would our data change from that? So the way in which the magnetic field, I guess, flows and how that would look if you were to model it computationally would look the same. It would just have a magnitude that's twice as large. So yeah, thanks for watching, and have a good day.